Let's get started. So, two sections to cover today. The first one is Newton's method, and then the second one is something we kind of already started, which is taking an antiderivative, the inverse of a derivative, undoing the derivative.
Isn't that just an integral though?
Yeah, it's an indefinite integral. We'll get down to the exact definition of an integral here in a bit, and right in the next chapter. So we'll be finishing up this chapter this week, and we'll go over exactly what an integral is next week. We call it an indefinite integral, an antiderivative, and that will make sense. But starting with Newton's method. So first off, maybe come back to this. If I have an equation like ax squared plus bx plus c, so y equals that thing. That's a quadratic equation. Quadratic because the highest power is 2. Something that we're often interested in with these equations is where are they equal to 0? And we've been doing a bunch of calculations where things are equal to 0. For example, when it's a derivative, we've been looking for where the derivative is 0 because that's something of interest. So if this were a derivative of an equation, then where this is 0, we may have a max or a min, for example. There's tons of applications where we're looking for where polynomials are equal to 0. So that's something we're very interested in. Now, if it's just a quadratic polynomial, you know how to calculate this. What is it? X is equal to, ready for L, negative b plus or minus the square root of b squared minus 4ac. Is this me pulling it out of the hat all over 2a?
Yeah.
That's called the Quadratic Formula or the Quadratic Equation.
It's been a while, but I remember it.
Yeah.
Is it ringing bells?
Yeah.
Okay, so now what about if we had an equation like ax cubed plus bx squared plus cx plus d, and we want to know where that's equal to 0. There's an equation for that. It's a lot bigger and hairier than this thing, but there is an equation for that. Okay? What about if we raise this to the 4, and we do 4, 3, 2, 1 plus e is equal to 0. Well, there's also an equation for that, and it gets even bigger and hairier. For me to write it out would take up the bottom half of this whiteboard. So it gets very big and hairy, but there's still an equation for that. Okay, so what about a 5th degree polynomial now? What about if we started it with a 5? If you start it with a 5 or higher, there is no formula. And there's provably no formula. It's not that we aren't smart enough to think up what the formula is. It's that we know that no such formula exists.
Why? Okay.
No, wait. So you'll just have to take my word for it that no such formula exists. Provably, no formula exists. So it's not that we're not clever enough. So when you have a 5th degree polynomial now, how on earth are we supposed to calculate where it's equal to 0? That's what Newton's method is going to help us with.
Okay.
And we do it by intelligent guessing. Since you can't just calculate it, you need a guess, and you need an intelligent way to guess. So Newton's method is an intelligent way at guessing the roots of equations. Okay? Now it's something that seems to confuse kids a lot, but it's honestly a pretty simple idea. Okay? So hopefully I've motivated why we need it. We can't just calculate everything. Okay. We can't just calculate everything, so we need other methods for calculating it. So let's say I've got some 5th degree polynomial. I have no clue what on earth it looks like, but there it goes. And it's a 5th degree polynomial or higher. Some equation. Here it is. With me so far?
Yeah.
So Newton's method Here, let me change the curvature here so that I can be on this side. So, here's that. It can come out, doesn't matter, but then I need this to kind of go like that. Okay, so I still need steeper, closer to the y axis. Let me change this down here. Should have done my curve first. Okay, something like that. Here's my xy axis. Good. Okay, so I'm looking for this point. I'm looking for where the polynomial is 0, right?
Okay.
Here's the essential idea behind Newton's method. First off, guess. Guess a point where it's 0. Just has to be kind of close. So our guess is going to be this point right here. Now so far that's way off, right?
Yeah.
Now, Newton's method, you do it over and over again. It takes your bad guess and slowly makes it better and better and better and better. And you can make it as good as you want.
Okay.
How good are you supposed to make it though?
It depends on how much you care. I mean, if we're talking about some equation and I calculate where the 0 is, say it's some real life equation modeling some particle, and I've got it within 4 decimal places in centimeters, is that good enough for the results I care about?
Probably.
If we're talking about protons moving through the air, no. If I'm talking about a ping pong ball moving through the air, yes, I overdid it.
I see.
So, whatever makes sense for what you're doing.
Okay.
But the point is, you can make it as good as you want, with some rare exceptions. For the most part, you can make it as good as you want. So we start out with x naught. Here it is. This is our guess. Now we calculate the tangent line of our polynomial at x naught. We know how to do that.
Mm-hmm.
We've done that 100 times. So at x naught, so we're saying at this point on here, so this right here, the height of this is f of x naught, right? With me so far?
Yeah.
So we're looking for the tangent line that goes through this point. Pretend that's it. What is the equation of this tangent line?
The equation?
Yeah. So y is equal to f prime of x naught, or m, times x minus x naught, plus f of x naught.
Yeah.
Just the equation of this tangent line.
Okay.
You see how I'm getting that?
No.
You're used to the equation y minus y naught is equal to mx minus x naught.
Mm-hmm.
This is the equation of a line that goes through the point x naught, y naught,
Okay.
with slope m.
Okay.
Replace y naught with y minus f of x naught. That's the y coordinate we want to go through.
Mm-hmm.
Is equal to, what's our slope? F prime of x naught. Times x minus, what's the x coordinate we want to go through? X naught.
Okay.
Okay. So then what we calculate is where this line, which is always just a line, a first degree polynomial,
Yeah.
we calculate where this thing intersects the x-axis. So we look for the 0 of this thing, which is going to be this point, right?
Yeah.
So I'm going to call this point right here x1.
Okay.
So let's figure out what x1 is. x1 is the x coordinate that makes my y 0. So I know that 0 is equal to, I know that if on this line, if y is 0, then x is equal to x1. So 0 is equal to f prime of x naught times x1 minus x naught plus f of x naught. You with me?
Yeah.
Mm-hmm.
Okay, so this is the equation for this tangent line. So any point I can plug in for x and y that makes this equation true must be on here. I just plugged in this point. This point is a point x1 comma 0 into this equation. Here it is.
Yeah.
Okay, I'm trying to solve for x1. Right?
Why are we trying to solve
X1 is going to be my next guess. Notice that x1 is now slightly closer to the actual root.
Okay.
So, if we solve for x1 here, what are we going to get? We're going to get, let's see, should have left this on the other side. Let's just distribute through. 0 is equal to f prime of x naught times x1 minus f prime of x naught times x naught plus f of x naught, right?
Yeah.
So I'm going to move these to the other side, but I'm going to write it backwards, so I'm going to write this term first. So f prime of x naught times x1 is equal to, we move these to the other side, so we get f prime of x naught minus f of x naught.
But f prime
No.
needs to be times
Yeah.
x naught.
Thank you. Let me get real sloppy with my writing. Equal to f prime of x naught times x naught minus f of x naught. Okay, now we're good, right?
Mm-hmm.
Okay? Divide through now by f prime of x naught.
Mm-hmm.
And so we get x1 is equal to x naught minus f of x naught over f prime of x naught. Follow that?
Yeah.
Okay, so now that gives me x1. Is x1 a good enough guess?
No.
Maybe it is, maybe it isn't. In our case, it doesn't really look like it is.
Yeah.
So we now repeat the process. I now find the tangent line at x1.
Okay.
Here's its tangent line. And then I find where it intersects the x-axis, called x2.
And it's the same formula?
And it's the same formula, so I know x2 is going to equal x1 minus f of x1 all over f prime at x1. Right?
Mm-hmm.
Okay.
And I could do it again and again and again and again. There's no limit to how many times I could do this, right?
Well, wouldn't you eventually just reach it?
Maybe, maybe not. But even if you do reach it, when I calculate the tangent line at that point, and then find where that tangent line intersects the x-axis, it's going to be at that point.
Yeah.
So I'd end up getting the same number over and over and over again.
And that's how you would know?
That you've reached it? Yeah, we won't talk about convergent series. That's a Calc 2 topic, but yes.
Okay.
So, anyways, in general, I can say your next guess is equal to your previous guess minus f at your previous guess over the derivative at your previous guess.
Okay.
So here's what you do over and over again, as many times as you want, to calculate the root. It's
Yeah.
called Newton's method, and that's all there is to it.
Okay.
That's what this whole section is about, just this one method.
And there's nothing new with it?
Well, now we can use it to approximate things. So we'll do, one exception. One case, it does not work if f prime at xn is equal to 0. If the derivative is 0, this method doesn't work. Now let's make sense out of why that doesn't work. So imagine I've got some curve that I want to know where it crosses the x-axis.
Okay.
And I happen to pick the point where the derivative is 0. What's the tangent line to that point? A horizontal line. Where does that intersect the x-axis? It doesn't. So if you happen to pick a point that has a derivative of 0, then you can't continue with the method because you can't calculate the next point where it intersects the x-axis.
And it makes intuitive sense because you can't divide by 0 either.
Right, so you can't divide by 0, which breaks the method, but I want you to see why geometrically it breaks the method.
Okay.
So it makes intuitive sense. You can't pick a point where the derivative is 0, right? But if you picked a point a little bit over here, you get closer and closer to that 0. If you picked a point a little bit over here, you get closer and closer to that 0. And then there are also special functions, super, super rare, but it can happen, where it gets you on a sort of a loop. So it can, hard to come up with just a picture of it. Hopefully the author has one of it. Yeah, he has one. Okay, so let me see if I can calculate it or draw this in. Give you intuition for it. Here's a tangent line. Here's a tangent line. And our function is going to look like so hard. Okay. Trying to there can also be very, very rare exceptions where you start at this point. You with me?
Mm-hmm.
Yeah.
No, that doesn't work. Here, you're gonna have to look at the picture. It's too hard to get it drawn perfectly. Maybe I can blow up the picture on here. Can you see that okay?
Yeah.
Mm-hmm.
Okay, so you start over here at x naught. Here's our function at x naught. Calculate the tangent at x naught, which goes through this point x1.
Okay.
Okay.
So then calculate the tangent at x1, which takes you back to this point x naught.
I see.
And so if you keep doing it, it ends up being a cycle. That's very, very rare, but that is possible.
Is that how it works with any x1, x0 you choose on that function?
No. So you picked an unlucky point.
Okay.
I think. Yeah, you picked an unlucky point. So, very rare exceptions, stuff like that. For the most part, it works. Chances are you won't be thrown any really weird problems where it doesn't work, and if it feels like it's not working, you just happen to pick a bad point. Try another point. Okay, so now let's do a couple examples. Say you don't have a calculator now, and I ask you, what's the square root of 2?
Root 2.
But what is it? What's the numeric approximation?
Isn't it like 1.3 something?
Well, let's say you don't know. So I send you back in time. The Greeks are asking you, hey, calculate this number for me. What are you going to do? Say, where's the closest calculator? No, you can use Newton's method now to calculate this thing. How can we use Newton's method to calculate this thing? We need to come up with a polynomial that has a 0 at the square root of 2.
Okay.
So, if I say f of x is equal to x squared minus 2, then where is that equal to 0? Then when 0 is equal to x squared minus 2 is where x squared is equal to 2. So it's where x is equal to plus or minus the square root of 2.
Yeah.
So the roots of this thing are the square root of 2. Where this thing's equal to 0 is the square root of 2. So I can use now Newton's method to approximate the square root of 2.
Okay.
So give me a guess for what, well, really quick, in Newton's method we need to use, let me write the equation again, up here. Let's just keep it up here. X sub n plus 1 is equal to x sub n minus f of x sub n all over f prime of x sub n, right?
Yeah.
Okay, so using Newton's method now, let's approximate this thing. Give me a guess for the square root of 2. Because what we're looking at is we're looking at an upside down parabola. goes through the point 2. So we're looking at an upside down parabola. And we're basically trying to calculate this x coordinate of this point, right?
Doesn't it go through the point -2?
No. Oh, it goes through the point, sorry, this should be root 2. So 1, we'll move up 1. And 2's up here. Here's 2, here's 1. Oh, -2, yes, you're right, sorry. This parabola's pointing up. Yes, you are absolutely right. Okay, parabola's pointing up. We only need half of it. We're looking for the x-coordinate of that thing, which we know is the square root of 2. But what's the numeric approximation? That's what we're going to calculate now. Okay, so give me a guess.
Any x?
Yeah.
You're asking? Okay, 1.5.
Well, let's start with just 1. Let's keep it simple to start with and see how the method works. So we're going to start with, we're going to guess 1. We know that's wrong, which is going to be here. We're going to calculate the tangent, which is going to pop us over here. And now we're probably going to get something closer to 1.5, right?
Yeah.
And then we'll calculate the tangent here, which will bring us back some and get us closer, and then we'll do it over and over again, getting closer and closer and closer. Now we don't need to draw the picture, we can just keep using the formula over and over again.
Okay.
So I'm going to say x naught is equal to 1. That's my first guess.
Okay.
So then my next guess, x1, is equal to x naught minus f of x naught. What's the value of my function at x naught?
-1.
-1. Now what's the derivative of my function?
Would be
2x.
2x, right?
Yeah.
So now what's f prime at x naught?
2.
2.
2. So this is equal to
1.5.
1.5. Wow, look at that, came out exactly. Okay, so now we do our next guess. x2 is equal to, might be easier to leave this as 3/2 for algebra.
Okay.
x2 is equal to x1 minus f at x1. What's f at x1?
1.
1.5 squared.
So 9/4 minus 8/4. Did I do that right?
Wait, isn't 3/2 squared just 3?
So we're looking for f of 3/2, right?
Yeah.
So that's going to be 3/2 squared
Oh.
You're right.
minus 2.
So 1/4.
So 1/4. So we're going to get 1/4 over f prime
It's 3.
is 3.
Oh, that's 3. There we go.
So this is equal to 3/2 minus a 12th.
Which is
Let's erase over here so that we can keep moving.
Which is
3/2 minus 1/12, which is equal to
5.
18 17/12. Did I do that right?
Yep.
Yeah, you did.
17/12.
Yeah.
So there's our next approximation of the square root of 2. Which is getting us closer. And we can keep doing this at infinitum, however many times we want, and getting closer and closer and closer. Might be tedious, but you know how to calculate those things. You know how to get a decimal approximation of that thing, right?
Yeah.
You know how to do 17 divided by 12. 12 goes into 17 one time, bring it down, minus we get 5, bring down to 0. How many times does 12 go into 5? 1.4. 0.4 times that gives me 48, minus is 2, bring down to 0. 1.41. And we can keep calculating this out, right?
Yeah.
Well, the actual numeric approximation of the square root of 2 is, it's got to be on here somewhere. Left my calculator home. Alright, plug it into Google. square root of 2, 1.414. So root 2, approximately 1.414. If we get to 3 decimal places, let's calculate one more decimal place on here and see how close we are. Right?
Yeah.
So 1, bring that down. We have 12 minus is going to be 8, bring down to 0. How many times is 12 going to 80?
6.
6.
72.
So we got 1.416 instead of 1.414. Look how close we are just after a couple times. And notice that we didn't even bother trying to get real close with our first guess.
Yeah.
And yeah, it still gets there pretty quick.
That's pretty neat.
Okay.
Okay? Feel like you could do that? Now you could do something like calculate the square root of 3 or something like that?
Yeah.
Okay. So let's look at another one. Now this, so far we've been talking about where this thing crosses the x-axis, where it's 0. Right?
Mm-hmm.
But we can still calculate it for any value that we want. We can calculate where it's 1, where it's 2, where it's 3, where it's 4. It's just we usually are interested in 0. And we can use the exact same method. So let's do an example like that. So we're supposed to find where the curve, hopefully I'm reading this right. I'm looking for where y equal to x cubed minus x crosses y equal to 1.
Okay.
So I'm looking for where that thing, where this is equal to 1.
Okay.
So I want to know where 1 is equal to x cubed minus x, right? Which is the same thing as where x cubed minus x minus 1 is equal to 0.
Yeah.
So I can always rewrite it with some new formula equal to 0. I can always move all my terms to one side, make it equal to 0.
Mm-hmm.
And then when I solve this, that's the same thing as solving this.
Yeah.
Wherever this is true, this is true. So Newton's method doesn't just tell you where your zeros are, it has a much broader application. You can calculate where a function's equal to any value you want. Make sense?
Mm-hmm.
So, now let's calculate this thing. This is what we're interested in. Let's use Newton's method to try and calculate it.
Okay.
Okay? Let's get a little bit of an idea of what this function's doing first, just for our own intuition, and then we'll start the calculation game. You with me?
Mm-hmm.
So let's see. If we plug 0 into this thing, what do we get?
Negative 1.
So if we plug in 0, we get negative 1. What do we get if we plug in 2?
5.
5.
Wait, are we plugging that in right? Because those are all equal to 0.
When you plug in 0, you get negative 1. Right?
Mm-hmm.
Oops. If we plug in 0. When you plug in 0, you get negative 1.
But the whole equation is equal to 0. Why? I'm saying, why don't you use the 1 where it's 1?
Oh, sorry. You're right. So the
Okay.
equation that we're interested in, yep, should have written this. F of x is equal to x cubed minus x minus 1. So now this is the equation we're interested in.
Okay.
And we're looking for the roots of this thing. Good point. Good point. So, sorry. So now we're looking for what's f of 0 equal to?
Negative 1.
Negative 1. And f of 1 will still be, what do I get when I plug in 1? Still negative 1.
Negative 1.
So f of 2,
5.
5.
Yeah.
So, just for our own intuition, I know that between 0 and 2, this thing has to have a root.
A root.
Somewhere where it's equal to 0.
Gotcha.
Because it's equal to negative 1 at 0, it's equal to 5 at 2, it had to cross the x-axis. So it has a root somewhere in there.
Okay.
Okay.
So, let me make sure he's not making another side point here.
Aren't we looking for when?
Oh, we could have done one better, sorry. F of 1 is equal to negative 1 as well. So between 1 and 2, we know there's a root.
That helps.
Okay, so between 1 and 2 is what we know. Now we're going to use Newton's method, throw in a guess, and get started with this thing. So, we'll start out guessing 1. Because, you know, it was kind of close. It gave us negative 1. It's close to 0.
Yeah.
So, we'll start out with x naught is equal to 1. Okay, so x1 now is equal to x naught minus f of x naught all over f prime of x naught. So, we need to figure out f prime real quick. What's f prime?
3x minus 1 times 3x squared minus 1.
F prime of x is equal to 3x squared minus 1, right? So this whole thing is equal to f of 1 is negative 1, right? F prime of 1
Is 2.
2. So this is equal to 3 halves. Well, oops, no, I did that wrong. It's equal to 3. Let's see. 1 minus f of 1 was negative 1, all over 2. Oh yeah, 3 halves. Did I do that right? So there's our next guess. 3 halves.
Okay.
And we're looking for when it gets closer to 0, right?
When it's equal to 0 is what we're looking for.
Okay.
And we know that at 1 it's negative 1 and at 2 it's 5. Now we can always check how close that thing is to 0 by plugging it back into our function.
That's right.
Right? So if you want to know how close is that guess, you can check that.
Okay.
But let's do one more. So x2 now is equal to x1 minus f of x1. What's f of x1? We're looking at this. Looking at this, we have 27/8 minus 3 halves, which is the same thing as 12/8,
Yeah.
minus 8/8. Is that right?
Yeah.
All over f prime at 3 halves. So that's going to be 27/4 minus 4/4. Right?
Okay.
Okay.
So let's simplify. So we still have 3 halves minus.
Hey, is it a good time to take pictures?
To take pictures, as in,
Oh,
Yeah.
that's right.
Christina, any pictures?
sure, give me one more minute.
Okay, they're ready as soon as you guys are.
Okay,
And Pauline says that you were invited to come down also and take a picture.
I'm okay. All right, so 27 minus 12 minus 8, that gives us 7/8, right?
Yeah.
All over 27 minus 4 is 23/4.
Okay.
Which can be equal to, we have 3 halves minus, times the reciprocal on that, we're going to get
28.
28, but, well, let's just write it so we can see the canceling better. Right? So that's going to be 7/46.
How'd you do that?
Took out the 4, right?
Oh, 4, if I cancel out 4 and 4, that just leaves 2.
Yeah.
Oh, I see.
So 8's the same as 4 times 2, which comes out like that, right?
It's 3 halves minus 7/46.
Oh, thank you. 3 halves minus that. Good. So then, let's see, where are we missing? 23, so 23 times 3, what is that? 69? So 69 minus 7,
62.
so it's equal to 62/46, which is equal to 31/23. So there's our next approximation.
Okay.
Okay, so Newton's method, you can plug that in to see how close it is. It's going to give you something really close to 0. Works pretty well. So that's the end of Newton's method. So go ahead, go get your pictures done, and when you come back, we'll do antiderivatives.
Okay.
Alright. Are they just in the study hall?
We struggled with 4.4 and 4.5 a lot. So I'm hoping you can help clarify that for me when we go over homework.
Sure.
You miss me?
So very much.
I figured. I tried to hurry.
Okay, I was talking to you in the future the whole time.
Let's see. Were you really?
Yeah. But I was. Now there's only one way to find out. Alright, so done with Newton's method. Now we're moving on to antiderivatives. Antiderivatives. Now, an antiderivative is just undoing a derivative. It's one way to think about it.
Okay?
And we already kind of started on this, right?
Mm-hmm.
So for each of these, I want you to calculate the derivative of them. So let's start with the top one. What's the derivative of the top thing? That's 1 over n plus 1 times x to the n plus 1 plus a constant. What's the derivative of that?
It's 1 over n times x to the power of n. Or,
No, times n plus 1 times
That's
x.
When I bring the n plus 1 down, then we're going to get n plus 1 over n plus 1 times x to the n
Why n plus 1 over n plus 1?
plus 0.
Oh, I see.
What do you do when you take the derivative? You bring down the exponent and subtract 1.
Wait, don't you have to take the derivative of the first as well?
There's only one term there we can take the derivative of. 1 over n plus 1 is just a constant.
because it's being multiplied by.
Okay.
Well, it's just a constant. That's,
Yeah.
We don't have the same thing up there as, if I know that y is a function in terms of x, I don't have something like x squared times cosine of x. That's not a constant, that's not a constant. Now we need to use a product rule.
Because n isn't a variable.
Yeah, 1 over n plus 1, n's not a variable, it's just
Okay.
some number, like 10, 15, 27. Okay, so this is its derivative, right?
Yeah.
Mm-hmm.
Which is equal to
X to the n.
just x to the n, right?
Yeah.
So now, another way of saying that is the integral of x to the n is equal to this.
Why?
If the derivative of this is equal to x to the n, then the integral of x to the n is equal to this. It's the opposite of a derivative. It gets you back where you started. That's what an antiderivative does. Start with this, take its derivative, that gives me this.
Mhm.
So if I take the integral of this, it has to be this. Because by definition, an antiderivative, an integral, undoes a derivative. It has to get you back where you started.
Can you explain why you're timesing it by dx and then why the sign?
The dx and that thing, just notation for saying, this says take the integral of that.
Okay.
We will give a precise definition for this notation in a second. You're fine.
Okay.
But now, if I were to ask you something like, what's the integral of x to the 7 with respect to x? This just tells you the variable you're integrating on. It tells you what's your variable. We're saying this function where x is our variable, we're integrating. It's the exact same as if I said, what's the derivative with respect to x of some function?
Gotcha.
That's different than taking the derivative with respect to w or any other variable.
Mm-hmm.
So the way dx is operating there is the same way dx is operating there.
I
It
see.
tells you what you're integrating with respect to. Okay, so what is it? What does our formula say? It says add 1 to the exponent
Mm-hmm.
and then divide by the exponent. Add 1 gives us 8, divide. So it's x to the 8 over 8 plus constant.
Okay.
Notice, take the derivative of this, what do we get? When we take the derivative, 8 comes down, cancels out with the 8, leaving 7. X to the 7 plus 0 is x to the 7.
Oh, because it's just a constant. Okay.
I mean, if it ever throws you off having a fraction with a constant, remember, you can always write that as 1/8 times x to the 8 if you prefer. And then just constant times a term. You know how to take the derivative of that, same way you know how to take the derivative of 3x squared. The
Yeah.
fact that the 3 is there shouldn't throw you off. The fact that 1/8 is there shouldn't throw you off.
Okay.
Good?
Yeah.
You got that?
Where's your, when you took the, no, I'm doing it. Yeah, that makes sense.
Make sense?
Yeah.
Okay. So now, let's do this one. K here is a constant, x is our variable.
So when you do the derivative.
So
of
what's the
minus-
derivative of the whole thing? The minus 1k we don't care about, that's just a constant, right?
Mhm.
Times, what's the derivative of cosine?
Negative sine
Negative sine
of k times x.
of k times x, chain rule,
Just K.
Times 1.
times k. The derivative of the inside is k. What's the derivative
Well,
of
k is just a constant. so
K
it
is just a
doesn't matter.
constant, yeah, that's K there. K. K is just a constant, like 7,
Oh,
right?
yeah.
So times K plus 0 for the constant, right?
Yeah.
What does that all equal?
Just should be okay.
Negative goes out with negative.
Mm-hmm.
That K cancels out with that K. And we're left with
Sine of k times x. Okay.
Over K.
sine of K times X, not over K. That K cancels out with that K.
Okay.
So what did we just figure out? We figured out that the integral of sine of kx with respect to x is equal to that. You'll learn to memorize these things, same way you do with derivatives.
Okay.
So, now let's think about this, just saying it. When I take the integral of sine, what's the thing that gives me sine when I take its derivative? Negative cosine, right?
Just cosine.
Negative cosine, when I take its derivative, gives me sine. I'm not saying what's the derivative of sine. I'm saying whose derivative is sine?
Oh, I see.
Negative cosines.
Yeah.
So when I'm looking for the integral of this thing, I know it's going to be negative cosine, and now instead of multiplying by a k like we do when we take the derivative, we divide by a k.
Okay, I think I'm getting it.
So when you apply the chain rule, when it's just constants, you divide instead of multiply.
I don't, how does that?
So let's calculate one really quick now. So let's say I'm looking for the integral of the sine of 3x with respect to x. With me?
Mm-hmm.
Ignoring the formula for a second and just kind of thinking it through. What gives me sine when I take its derivative?
Negative cosine.
Negative cosine. And now if I were taking a derivative, I'd multiply by 3, right? So when I take an antiderivative, or an integral, I divide by 3,
Okay.
plus constant.
That's it?
That's it. And then if you look at the formula, exact same thing. Replace your k with 3.
Okay.
So it's good to have the formula, but it's also good to connect it with your intuition.
Yeah.
Alright, let's do the next one. 1 over k times sine of kx. Let's look at its derivative. So we're looking at the derivative of 1 over k times sine of kx plus a constant. We're looking for its derivative with respect to x of this whole thing. Okay, what's that equal to?
Just cosine of k times x times k.
But then we have our 1 over k.
Cancels out,
So we also need our 1 over k, right?
which is just 1.
Which that will end up being 1, and then plus 0, right?
So it's just cosine of k times x.
Just cosine of k times x. So in other words, the integral of cosine of k times x with respect to x is equal to that thing.
Okay.
Okay? Next. What's the derivative of this thing? So 1 over k, that's still just a constant, so we have 1 over k times, what's the derivative of tangent?
Isn't it like negative?
No, positive. Cotangent's one that gives you negative.
Just 1 over cotangent then?
No.
Oh, it's
Derivative of tangent is
tangent times.
secant squared.
I knew that.
Why don't you say it?
I'll just wait for you to.
Secant squared of k times x times what? Chain rule,
Oh, okay.
which is equal to just secant squared of k times x. So now we know the integral of secant squared. So the integral of secant squared of x, or k times x, with respect to x is equal to that. Similarly, when you calculate this one, it's going to be the integral of cosecant squared of k times x. With respect to x, we'll give you that one. So we don't need to calculate that one. And then we'll do secant and then just write cosecant. So what's the derivative of this thing?
The secant is equal to
It's secant times tangent.
yeah.
So secant of k times x times tangent of k times x
Times k.
times k. K's go out. And so we're left with, write out, secant of k times x times tangent of k times x. So what did we just calculate? We just really showed that the integral of secant of k times x times tangent of k times x with respect to x is equal to that thing. And similarly, the integral of cosecant of k times x times cotangent of k times x with respect to x will be equal to that thing. Okay? So those are all the formulas that it gives you. And you can use the formulas, but it's better to just memorize what the derivatives of these things are and then just logic through it. Memorize your derivatives for the 6 trig functions, and then you can just think up the integrals in your own head. Okay, so now let's solve each of these problems. These are all the example problems, with the exception of one word problem that was a physics problem. So we'll do these, go back to the physics problem, and then we're done.
Okay.
Okay, so let's look at the first one. What's the integral of x to the 5 with respect to x?
X to the 4.
All right, Peter, you're up. You do come right now. I can't stand anymore. All right. So let's do the first one. Jeremy, who needs help?
What's that?
These are all in your book.
Isn't it just x to the 6 over 5?
Over 5?
Over 6.
Over 6. Jeremy's going to check your math. X to the 6 over 6. Almost. You need all possible solutions. We went over pretty extensively last class why we always have to have that plus c, right?
Yeah.
So if two functions have the same derivative, then they differ by a constant. So you found the family of solutions, all possible solutions to that equation. That's why we call that an indefinite integral is what you're calculating. Indefinite meaning we're not getting an exact solution, we're getting a family of solutions.
And next section we're going to be
We'll talk about definite integrals,
where we know what this is.
where you can calculate the constant. Yes.
Okay.
Okay, so moving to the right, plus the integral of the square root of x.
Most equal to just 1/2.
Yeah, that's the same thing as x to the 1/2. So, what's its integral?
X to the 1/2.
So x.
The
to
square root of
3/2.
x is the same thing as x to the 1/2.
Oh, so it's
X to the
3/2
over.
Divided by 3/2 or times 2/3.
does it matter which way you write it?
Well, you're going to simplify. So x to the 3/2, all over 3/2 if you want, plus constant. And then when you simplify, it's just whichever way you want to write it. You can write 2x to 3/2 over 3. Okay, if you write it that way, convention, the coefficient always goes in front of the variable.
That's right.
That way you'll never mix it up with the exponent. So 2/3 x to the 3/2 plus constant. Sure. Okay, next let's do sine of 2x. Let's see, don't look at the formula. See if you can do it without the formula and just think about it. Whose derivative is sine? Feel free to
Cosine.
rewrite it lower if you want some space.
Oh, right.
Whose derivative is sine?
Negative cosine, right?
Negative cosine. So you know it's going to have a negative cosine of 2x in there.
Yeah, okay. Negative cosine of 2x times 2.
You're not calculating its derivative. You're
Oh,
calculating its
that's right.
antiderivative. So whose derivative is sine? Negative cosine,
Mm-hmm.
right? So you know it's going to be negative cosine of 2x. Will be in there.
Yeah,
Instead of multiplying by 2, it's being
And now
divided
instead of
by
multiplying by 2, you divide by 2.
that's right.
So negative cosine of 2x divided by 2. That's constant. Good. Next one. Cosine of x over 2.
Just sine.
Sine of x over 2. But then what do we divide by?
You multiply by 2.
Multiply by 2.
Multiply by 2. Same as dividing by 1/2. Yep.
Okay.
Sorry.
No, 2. You would
Oh,
divide
2.
by
Yeah,
1/2.
divide by 1/2 times 2.
Which is the same as times in 2. Good. Okay, that next one, the integral of 3 squareds of x plus sine of 2x. Now,
You split it up, right? I'm saying like you would for a derivative with the plus. You
yes.
would just split it up.
Integral
So-
plus an integral.
when we come up with the exact definition of an integral, well, that'll be a definite integral. Indefinite integrals follow the same rules as definite integrals. Definite integrals are just limits. And since the limit of a sum is the sum of the limits, then an integral of a sum is the sum of the integrals.
Okay.
So I can rewrite that. That's equal to the integral of 3 squareds of x. The integral of 3 squareds of x
Square roots of x,
with
right?
respect to x, dx. Get rid of your first parenthesis. Plus the integral
I see.
of the sine of 2x with respect to x. Now you can calculate each of those separately.
Yeah, this one is, what the heck? 3
That's the first.
3 times x to the 1/2, which is 3 to the x to the 3 over 2, right?
You might be thinking right, but you said it right, but your brain might be in the right place.
Like that. Over
Divided by,
3 over 2.
yep, divided by 3 halves. So that's equal to,
2/3 times 3 is just 2.
correct.
So that's equal to 6.
No, just 2. You already used
You got rid
Oh,
of it.
yeah. 2x to the 3 halves.
Okay.
Plus c. And
Plus
then this
that
one is negative cosine
Mm-hmm.
of 2x over 2.
Mm-hmm.
And that's
Plus
it.
a constant.
Plus constant.
Now, you call one constant C1 and call the other constant C2. C sub 1, C
Yeah,
sub
because
2.
they're not the same constant.
Right, so when we write the whole thing, now what is a constant plus a constant?
Just a constant.
Just a constant. So now I can rewrite the whole thing as 2x cubed
Let me
minus
just-
cosine of 2x is equal to c. Yeah, if you're doing well, just do c.
Okay.
C sub x makes it seem like they're iterating over something. So then you get the whole thing is 2x to 3 halves minus cosine of 2x
Over 2.
over 2 plus c.
Plus-
And there you go.
Okay.
Okay,
Seems
last
straightforward.
one. See if you can do that one all in one go. See if
In
you can
one go?
write the solution.
That's just,
X 3 over 3.
yeah, x 3 over 3 minus x squared over 2, 2x squared over 2 plus,
Oh, what do we do with a constant?
isn't that just 5x over 5?
5x over 1.
Which is just 5x.
Perfect. Good job. You didn't get thrown for a loop. Missing one thing
You can see.
plus a constant. We're looking for all possible solutions.
You could just get rid of the 2's on the x squared.
Yep.
Oh, that's right.
Good.
Nice.
Okay, so those were all the examples, and then we had one physics problem that we'll do, and then we're done.
Okay.
So let's read the physics problem. A hot air balloon ascending at the rate of 12 feet per second. So I'm kind of write down what I know as we go. And this is probably enough space. Well, we might need a rock picture. Okay. So we got a hot air balloon. And it's moving up at 12 feet per second, right?
Mm-hmm.
Or in other words, I know that my velocity with respect to time, oh, it could be changed in this time domain. So, let's see. A hot air balloon is ascending at a rate of 12 feet per second, and it's at a height of 80 feet. So we're 80 feet above the ground. A hot air balloon ascending at a rate of 12 feet per second is at a height of 80 feet above the ground when a package is dropped. How long does it take the package to reach the ground? Okay, so here you are, you're in a hot air balloon. You know you're going up 12 feet per second.
Mm-hmm.
So you drop a package. out of the hot air balloon
At 80 feet?
when it's at 80 feet, when's the package going to hit the ground? So remember that, keep this in mind, the instant you let go of the package, it starts falling to the ground, right? It starts moving down.
Mm-hmm.
No! The instant you let go of the package, it's still moving up because the hot air balloon is moving up. To you, the instant you let go of it, it's not moving, but you and the package are both moving up. To someone on the ground watching this, what's the package going to do? It's going to go up and then fall when you let go of it.
That's for real?
It
It doesn't
still
just fall
has
instantly?
momentum.
Yeah.
Oh, that makes sense.
Here's another way to think about it. A similar idea. Imagine you're sitting in the back of a truck.
Okay.
The back of the truck is driving really fast.
Mm-hmm.
In the back of the truck you have a ball. You throw the ball up and it falls back down in your hands, right?
Mm-hmm.
Yeah.
To someone outside the truck, what happened? You threw the ball up and it came back down in the truck.
Same thing if you were to
Sorry, I
jump
should
off
get the camera.
right?
So you in the back of the truck, so the truck is moving along, so it's right here, moving along, and it moves to here by the time the ball comes back down. So you in the back of the truck, to you it just went up and down, but to someone outside the truck, the ball's path went like this.
That's pretty neat.
Interesting.
Make sense? So here you are in a hot air balloon. Another way you can think about it is, here we are on the surface of the Earth. The Earth is rotating from west to east at 1,000 miles per hour, roughly. Watch the marker. Well, that was good. But imagine I threw the marker up so high that it took an hour for it to fall back down. Right?
Okay.
So to us, it went straight up and down. But then if you're outside the Earth, watching the Earth spin, it also traveled 1,000 miles. Assuming we're on the equator.
Yeah.
Make sense?
Mm-hmm.
Okay, so you're in the hot air balloon. You drop a package. The instant you let it go, relative to you, it's not moving, right? The instant I let this go, it's not falling.
Mm-hmm.
It takes a little bit of time.
You mean the second you let go, it's still there? Or that the momentum moves?
The instant I let it go, it's not moving,
Okay.
right?
Yeah.
It takes time for it to gather speed, and start moving. So the very instant we let it go, it's not moving, relative to me. So if I'm holding the package and I'm in a hot air balloon, the very instant I let go of the package, it's not moving relative to me, but I'm moving up at 12 feet per second. So my package starts moving up at 12 feet per second.
Okay.
But it has gravity pulling on it. We're in a hot air balloon, that's going to keep this going up at a constant rate of 12 feet per second. The package is experiencing gravity, so it's going to slow down, and then fall back down to the Earth.
Yeah.
So if we plot its position with respect to time, it's going to look like this. That's not the path it takes, that's its position with respect to time.
Mm-hmm.
So at 0 seconds, it's going to be 80 feet up. At 1 second, it's going to be like 90 feet up. 2 seconds, it's going to reach its height. And then 3, 4, 5, 6, 7, however long, hit the ground.
Are you just saying 2 seconds for the example?
I'm just throwing out a number. We are going to calculate what all these C's are. Okay, so you understand what's going on, right?
Yeah.
So notice that we have no clue what our position function looks like. Right?
Yeah.
No clue what that looks like. But I do know that S at 0 is equal to what?
80.
80.
Mm-hmm.
At time 0, our package is 80 feet in the air.
Okay.
Similarly, I have no clue what my velocity function looks like. But I do know that my velocity at 0 is equal to
12.
12. The velocity of the package, the instant I let it go, is moving up at 12 feet per second.
Yeah.
So the velocity at time 0 is 12. We're going to call the up direction positive and the down direction negative. With me?
Yeah.
But I have no clue what this velocity function looks like. and this is just an experimental fact, if we have it in feet per second, is minus 32 feet per second squared. Or we'll ignore units for now and just say minus 32.
That's your acceleration.
That's an experimental fact. So Galileo went out there and he measured, and he says all objects accelerate to the Earth at negative 32 feet per second squared. So that's an experimental fact, something that was discovered in a lab with experimentation and careful measuring.
Okay.
So we do know this. This is the case for any object anywhere on Earth. It accelerates downwards at 9.81 meters per second. Sorry, we have feet. At negative 32 feet per second squared.
Yeah.
Okay? That's an experimental fact. So we need to figure out what this looks like and what this looks like with this information.
You could just take antiderivatives.
And you can take antiderivatives because remember that the velocity is the same thing as the s prime of t. Velocity is the change in position.
Yeah.
And similarly, acceleration is a change in velocity. So this is a derivative of this, this is a derivative of this.
Okay.
What?
So to get my velocity from my acceleration, I need to integrate.
Mhm.
You with me?
What is the question asking us to do?
We're trying to figure out when the package is going to hit the ground.
So we have to get those, and then
So I need to know when s of t is equal to 0, but I don't even know what s of t is.
yeah.
So I need to figure out s of t.
Okay.
So start out with a of t, integrate it to get b of t, integrate that to get s of t. You with me?
Mhm.
So we start with a of t, we need to integrate this thing. So if I do the integral of a of t with respect to time, then I know that this is v of t.
Yeah.
Make sense?
Mhm.
So that's what we're going to calculate. So what is the integral of negative 32 with respect to time?
Just
Be
negative
negative
32.
32t plus c.
Negative 32t plus some constant.
Yeah.
But we,
Now notice that the constant, this constant, t naught is what I'm going to call it, this constant, and this is also equal to v of t. Okay, right?
Mhm.
yeah.
Now, since, what does v of t give me when I plug in 0? Let me just put c here for a second, then we'll go back. So I know that the integral of this thing is negative 32t plus c, right? So that's what vt is. But I don't know what that constant is. But when I plug in 0 for t, what do I get?
You get 12.
You get 12.
I get c.
C.
Yeah, you get C, but
You get c, but you're looking over there and saying c is 12, right? Ignore that right-hand information for a second.
okay.
So notice that v of 0 would just be my constant c.
Yeah.
So in physics, we call this constant v naught, which is the velocity at time 0. And that's why we call it v naught. It's your velocity at time 0.
That makes sense.
Your constant will always be your velocity at time 0 in this equation.
Okay.
So we call it v naught. Good? So that's how, I'm just getting you comfortable with the notation so that down the road when you see a v naught or an s naught, you're not going to get confused. Okay, so now we know what that v naught is. We know, as you said, oh, it has to be 12, right? So I now know that this is negative 32t plus 12.
Okay.
Now the way we actually prefer to write it in physics is the constant first, so 12 minus 32t. For some reason in physics we write our polynomials in increasing order instead of decreasing order.
Okay.
But same thing, right? Okay, now we need s of t. Well, s of t is going to be the integral of v of t, and then we'll use that to get our constant.
Okay.
And just terminology, we call the fact that s naught, or s of 0 is equal to 80 and v of 0 is equal to 12, we call those initial conditions. So if I say now when we look at our initial conditions, you know what I'm talking about.
Okay.
So we know that s of t is equal to the integral of v of t with respect to t, which is equal to the integral of negative 32t, or 12 minus 32t. with respect to t, right?
Mhm.
Which is equal to what?
12t
12t
minus 32t, no, minus,
Plus 16
that's not.
minus 16
t squared
t squared plus our constant, right?
s.
Course.
Our constant s naught, which in our case we know is going to be 80.
Yeah.
Yeah.
Okay, so s of t is equal to 80
Plus.
plus 12t minus 16t squared. Good?
Mhm.
Okay, so now, notice what we were able to do. Just knowing the acceleration and what the velocity and position were at one time, we now know what these things look like indefinitely. I can now calculate their velocity and position at any time you want.
And we're looking at ground level, right?
Now we're looking at ground level. So I want to know where is this thing going to hit the ground,
Okay.
right? Which is asking the same question as what?
How much time did it take?
Yeah, how much, when does it hit the ground? But what do I know about when the package hits the ground? How high is it?
0.
So what's s of t?
Yeah.
0. So I want to know where is this equal to 0?
Oh, I see.
So I want to know where
Okay.
80 plus 12t minus 16t squared is equal to 0. Where does that happen? Well, really quick, let's factor out, what can we factor out? At least a 4.
Yeah.
So we can rewrite this as 4 times 20 plus 3t minus 4t squared, right?
Yeah.
And now, you could divide both sides by 4 if you want and just get rid of that 4 altogether. Good?
Yep.
And now we'll just use the quadratic equation rather than trying to think about how to factor this thing. So using the quadratic equation, we know that t is equal to
B. What's your B?
negative b, the coefficient of this, a, b, c.
Why negative? Oh, negative. Yep.
Negative b plus or minus the square root of b squared minus 4a, that one's a, c, all over 2a.
Okay.
With me? Just using the quadratic equation. And this is equal to negative 3 plus or minus the square root of, let's see, 4 times 20
80.
is
Negative
80. 320 plus 9, 329.
Yeah.
I wonder if that comes out evenly. All over negative 8. 329. What could that be squared? Doesn't come out evenly. I wonder if we made a mistake. Let's see. Negative 16t squared plus 12t plus 80. That's what we got. Negative 3 plus or minus the square root of 329 over negative 8. Okay. Which gives us, when we take the positive case, we get a negative number. When we take the negative case, we get a positive number. So notice that there's two solutions to this thing, right? So the two solutions are going to be t roughly, because this doesn't come out evenly, roughly negative 1.89 and t roughly 2.64. Those are the two places where this is 0. Now why do we get two solutions to this thing?
I don't know.
This is an upside down parabola. So this is saying, we're saying that our package from time 0 onwards looks like this until it hits the ground. So this is only valid for times between 0 and until it hits the ground. Right? This equation isn't valid for negative times. If I were to plug in negative 10,000, what is this going to tell me? It's going to tell me, oh, your package was in the center of the earth. Which doesn't make sense.
Yeah,
Because my equation doesn't know the physics of what's going on.
but you have to.
So my equation says, if we graph this thing, it's an upside down parabola. Like this, right?
Yeah,
And our package started right here at time equal to 0. Should have drawn that better. Here's the axis we care about. Our package starts right here at time equal to 0. We drop it. It goes up some and then goes down. But we know because of the physics of the problem that this part of the equation doesn't make sense. And it doesn't make sense to go beyond the ground. Right? So you have to do a little bit of your own thinking in where this equation is valid.
which is this.
And it's only valid right here.
Okay.
Right? So you can't blindly say, okay, now I know where this package is going to be in 10 years. Right?
Mhm.
You plug in 10 years, it's going to have fallen through the earth and been well on its way.
Yeah.
Which doesn't make sense. So it's only valid on this range. So obviously the time that we care about is 2.64 seconds.
That's the amount of time it takes.
Yeah, that's when the package will be at height 0.
That's kind of fast.
Yeah, things fall fast.
And if it was a heavy package, it would have.
Fallen a lot faster, right?
Mhm.
No.
We've had this discussion, but isn't it with air resistance or something like that?
Then that depends on the aerodynamics of what you're dropping, the density of what you're dropping. Yeah, a lot of things come into play. But as a general rule, if you ignore air resistance, all objects accelerate downwards at the exact same rate.
Okay, I know why
And
that
we'll
works.
prove
but
that.
Why is that the case?
We will prove that in physics.
We will?
We will prove it.
Awesome. Okay.
So,
Well, just intuitively, how does that make sense? Does the Earth just pull everything at the same
no.
speed?
Earth is a common.
It doesn't pull it with the same force. The Earth exerts a wave, so gravitational force is proportional to mass. The more mass you have, the more gravity you exert.
Yeah.
Good with that idea?
Mhm.
Okay.
Okay. So let's imagine that you have the Earth and the Sun, and we're going to pretend that we're standing on the Sun now, and somehow this is possible, holding up the Earth. We're going to drop the Earth and we're going to drop you. We're going to measure you falling on the Sun, and you're both going to fall at the same rate. Stick with me for a second.
Okay.
The Sun exerts a way bigger force on the Earth than it exerts on you, pulling you downwards. But mass is also an object's resistance to move. What's harder to push? A big boulder or a little pebble?
The boulder.
The boulder's harder to
Harder
push.
to push, yeah. So-
Harder to push. What's harder to move? What's harder to get moving? Imagine that you have like a mining cart that's perfectly frictionless, right? And you have to get this mining cart moving. Is it easier to get an empty mining cart moving or a mining cart that's completely full of ore?
Empty.
The empty one. The more mass something has, the harder it is to make it accelerate. Mass is an object's resistance to accelerate.
Okay.
It's hard to change its speed. Once I get its speed, now it's hard to stop it.
Yeah.
It's hard to change its speed.
Mhm.
Mass is an object's resistance to accelerate. So while the Earth pulls a big rock a lot harder, with a lot more force than it pulls a little rock, a big rock also resists a lot more than a little rock.
Okay.
So how hard it pulls a big rock is proportional to its mass, but how hard the big rock resists is also proportional to its mass. And so the mass cancels out.
What the heck? So it's like algebra, okay.
And so all objects get pulled towards the Earth with the same acceleration.
Because in a sense, the two masses.
Sorry, you don't know that force is mass times acceleration.
Yeah.
Should have given you that. Force is equal to mass times acceleration. That's what force is. Okay.
Okay.
So the Earth pulls me. Let's pretend I'm a big fat guy, you're a skinny guy.
Okay.
So the Earth would pull me with a lot more force than it would pull you because I'm a lot bigger.
Okay.
But since I have a lot more mass, so how hard it pulls me is proportional to my mass. So that force is going to be my mass times my acceleration. But how much I resist is proportional to my mass. And so those cancel out, leaving just the acceleration.
Oh.
You can't read too much into this equation, but that's what I meant by when the masses cancel out, you're left with just the acceleration. Because force is mass times acceleration, one of Newton's 3 laws.
Interesting.
Anyways, yeah, we'll prove all that. That will make a lot more sense. I mean, we haven't even talked about what force is. Skipping clear to chapter 6 of our book, I think.
Of physics?
Yeah, but physics we'll go through a chapter every class.
Oh.
So it's not like this class.
Oh.
A chapter in physics is like 2 to 3 sections of this book.
So that makes sense.
Anyways. We finished last problem. Sorry. Probably should have turned off the lecture before we went on that tangent. We're done with material.
Oh.
So that's the end of chapter 4.